Hi friends, in our earlier discussion we talked about the TTL logic families, their characteristics, operation and usage. In today's lecture we shall discuss about CMOS logic families. The CMOS or the complementary metal oxide semiconductor logic family uses both N type and P type MOSFETs to realize different logic functions. The two types of MOSFET are designed to have matching characteristics, that is, they exhibit identical characteristics in switch off and switch on conditions. The main advantage of CMOS logic family over bipolar logic families discussed so far lies in its extremely low power dissipation, which is non-zero in static conditions. In fact, CMOS devices draw power only when they are switching. This allows integration of a much large number of CMOS gates on a chip than would have been possible with bipolar. CMOS technology today is the dominant semiconductor technology used for making microprocessors, memory devices and application specific integrated circuits. The CMOS logic family, like TTL, has a large number of subfamilies. The basic difference between different CMOS logic families is in the fabrication process used and not in the design of the circuits employed to implement the intended logic function. We will firstly look at the circuit implementation of various logic functions in CMOS and then follow this up with a brief description of different subfamilies of CMOS logic. Circuit implementation of logic functions. In our discussion here, we will briefly talk about the internal schematics of basic logic functions when implemented in CMOS logic. These include inverter, NAND, NOR, AND, OR, XOR, XNOR and or invert functions. CMOS inverter. As shown in the figure, the inverter is the most fundamental building block of CMOS logic. It consists of a pair of N-channel and P-channel MOSFETs connected in cascade configuration. When the input is in the high state, P-channel MOSFET Q1 is in the cutoff state, while the N-channel MOSFET Q2 is conducting. The conducting MOSFET provides a path from ground to output and the output is low. When the input is in the low state, Q1 is in conduction while Q2 is in cutoff. The conducting P-channel device provides a path for VDD to appear at the output, so that the output is in high or logic 1 state. A floating input could lead to the conduction of both MOSFETs and a short circuit condition. It should therefore be avoided. It is also evident from figure that there is no conduction path between VDD and ground in either of the input conditions, that is, when input is in logic 1 or 0 states. That is why there is practically zero power dissipation in static conditions. There is only dynamic power dissipation, which occurs during switching operations as the MOSFET gate capacitance is charged and discharged. The power dissipation is directly proportional to the switching frequency. NAND gate. Figure here shows the basic circuit implementation of a 2-input NAND. Two P-channel MOSFETs Q1 and Q2 are connected in parallel between VDD and the output terminal, and two N-channel MOSFETs Q3 and Q4 are connected in series between ground and output terminal. For the output to be in logic 0 state, it is essential that both the series connected N-channel devices conduct and both the parallel connected P-channel devices remain in the cutoff state. This is possible only when both the inputs are in logic 1 state. This verifies one of the entries of the NAND gate truth table. When both the inputs are in logic 0 state, both the N-channel devices are non-conducting and both the P-channel devices are conducting, which produces logic 1 at the output. This verifies another entry of the NAND truth table. For the remaining two input combinations, either of the two N-channel devices will be non-conducting and either of the two parallel P-channel devices will be conducting. We have either Q3 off and Q2 on, or Q4 off and Q1 on. The output in both cases is a logic 1, which verifies the remaining entries of the truth table. From the circuit schematic, we can visualize that under no possible input combination of logic states is there a direct conduction path between VDD and ground. This further confirms that there is near zero power dissipation in CMOS gates under static conditions. NOR gate. Figure shows the basic circuit implementation of a two input NOR. As shown in the figure, two P-channel MOSFETs Q1 and Q2 are connected in series between VDD and the output terminal, and two N-channel MOSFETs Q3 and Q4 are connected in parallel between ground and output terminal. For the output to be in logic 1 state, it is essential that both the series connected P-channel devices conduct and both parallel connected N-channel devices remain in the cutoff state. This is possible only when both the inputs are in logic 0 state. This verifies one of the entries of the NOR gate truth table. When both the inputs are in logic 1 state, both the N-channel devices are conducting and both the P-channel devices are non-conducting, which produces logic 0 at the output. This verifies another entry of the NOR truth table. For the remaining two input combinations, either of the two parallel N-channel devices will be conducting and either of the two series connected P-channel devices will be non-conducting. We have either Q1 off and Q3 on, or Q2 off and Q4 on. The output in both cases is logic 0, which verifies the remaining entries of the truth table. OR gate and AND gate. An and the OR gate is nothing but a NAND gate followed by an inverter. Figure shows the internal schematic of a two input AND in CMOS. A buffered AND gate is fabricated by using a NOR gate schematic with inverters at both of its inputs and its output feeding two series connected inverters. The figure here shows the internal schematic of a two input OR in CMOS. A buffered OR gate is fabricated by using a NAND gate schematic with inverters at both of its inputs and its output feeding two series connected inverters. And or invert and or and invert gates. The figure shows the internal schematic of a typical 2 wide 2 input and or invert gate. The output of this gate can be logically expressed by the Boolean equation where y is equal to a dot b plus c dot d whole bar. From this expression, we can say that the output should be in a logic 0 state for the following input conditions. When either a dot b is equal to logic 1 or c dot d is equal to logic 1, when both a dot b and c dot d equal logic 1. For both these conditions, there is a conduction path available from ground to output, which verifies that the circuit satisfies the logic expression. Also, according to the logic expression for the AND or invert gate, the output should be in logic 1 state when both A dot B and C dot D equal logic 0. This implies that either A or B or both are in logic 0 state, or either C or D or both are in logic 0 state. If these conditions are applied to the circuit of figure, we find that the ground will remain disconnected from the output and also that there is always a path from VDD to output. This leads to logic 1 at the output. Thus, we have proved that the given circuit implements the intended logic expression for the AND or invert gate. The OR and invert gate can also be implemented in the same way. Figure shows a typical internal schematic of a 2 wide 2 input OR and invert gate. The output of this gate can be expressed by the Boolean equation y is equal to a plus b dot c plus d whole bar. It is very simple to draw the internal schematic of an AND or invert or OR and invert gate. The circuit has two parts, that is the N channel MOSFET part of the circuit and the P channel part of the circuit. The two parallel arrangements are connected in series to achieve an ANDing operation. The complementary P channel MOSFET section achieves inversion. Note that the P channel section is the complement of the N channel section with N channel MOSFETs replaced by P channel MOSFETs and parallel connection replaced by series connection and vice versa. Transmission gate. The transmission gate, also called the bilateral switch, is exclusive to CMOS logic and does not have a counterpart in the TTL and ECL families. It is essentially a single pole single throw switch. The opening and closing operations can be controlled by externally applied logic levels. Figure shows the circuit symbol. If logic 0 at the control input corresponds to an open switch, then logic 1 corresponds to a closed switch and vice versa. The internal schematic of a transmission gate is a parallel connection of N channel MOSFET and a P channel MOSFET with the control input applied to the gates. Control inputs to the gate terminals of two MOSFETs are the complement of each other. This is ensured by an inbuilt inverter. When the control input is high, both devices are conducting and the switch is closed. When the control input is low, both devices are open and therefore the switch is open. It may be mentioned here that there is no discrimination between input and output terminals. Either of the two can be treated as the input terminals for the purpose of applying input. This is made possible by the symmetry of the two MOSFETs. It may also be mentioned here that the on resistance of a conducting MOSFET depends upon drain and source voltages. In the case of an N channel MOSFET, if the source voltage is close to VDD, there is an increase in on resistance leading to an increased voltage drop across the switch. A similar phenomena is observed when the source voltage of a P channel MOSFET is close to ground. Such behavior causes no problem in static CMOS logic gates, where source terminals of all N channel MOSFETs are connected to ground and source terminals of all P channel MOSFETs are connected to VDD. This would cause a problem if a single N channel or P channel device were used as a switch. Such a problem is overcome with the use of parallel connection of N channel and P channel devices. Transmission gate devices are available in 4000 series as well as 74 HC series of CMOS logic. CMOS with open drain outputs. The output of conventional CMOS gates should never be shorted together as illustrated by the case of two inverters shorted at the output terminals. If the input conditions are such that the output of one inverter is high and that of the other is low, the output circuit is then like a voltage divider network with two identical resistors equal to the on resistance of a conducting MOSFET. The output is then approximately equal to VDD by 2, which lies in the intermediate range and is therefore unacceptable. Also, an arrangement like this draws excessive current and could lead to device damage. This problem does not exist in CMOS gates with open drain outputs. Such a device is the counterpart to gates with open collector outputs in the TTL family. Figure here shows the internal schematic of a CMOS inverter with an open drain output. The output stage of a CMOS gate with an open drain output is a single N channel MOSFET with an open drain terminal, and there is no P channel MOSFET. The open drain terminal needs to be connected to VDD through an external pull-up resistor. The pull-up resistor shown in the circuit is external to device. Input protection. Owing to the high input impedance of CMOS devices, they are highly susceptible to static charge buildup. As a result of this, voltage developed across the input terminals could become sufficiently high to cause dielectric breakdown of the gate oxide layer. In order to protect the devices from this static charge buildup and its damaging consequences, the inputs of CMOS devices are protected by using a suitable resistor diode network as shown in this figure. The protection circuit shown is typically used in metal gate MOSFETs such as those used in 4000 series CMOS devices. Diode D2 limits the positive voltage surge to VDD plus 0.7 volt, while diode D3 clamps the negative voltage surge to minus 0.7 volt. Resistor R1 limits the static discharge current amplitude and thus prevents any damagingly large voltage from being directly applied to the input terminals. Diode D1 does not contribute to input protection. It is a distributed PN junction present owing to the diffusion process used for fabrication of resistor R1. The protection diodes remain reverse biased for the normal input voltage range of 0 to VDD and therefore do not affect normal operation. The figure here shows a typical input protection circuit used in 74C, 74HC etc. series CMOS devices. A distributed PN junction is absent owing to R1 being a polysilicon resistor. Diode D1 and D2 do the same job as diode D2 and D3 as in the case of metal gate devices. Diode D2 is usually fabricated in the form of a bipolar transistor with its collector and base terminals shorted. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. The CMOS logic family uses both N-type and P-type MOSFETs to realize different logic functions. The two types of MOSFET are designed to have identical characteristics in switch off and switch on conditions. The main advantage of CMOS logic family over bipolar logic families discussed so far lies in its extremely low power dissipation, which is non-zero in static conditions. This allows integration of a much large number of CMOS gates on a single chip. CMOS technology today is the dominant semiconductor technology used for making microprocessors, memory devices and application specific integrated circuits. So, that is it for today. See you in the next lecture. Thank you very much.